And in my box tomorrow at 9, where it goes.
Your password.
You don't update automatically, but yes, I did have to. Okay, so just kind of a quick we're going to spend more time talking about section 7.3. In particular, we're going to spend time talking about what's a better way to check for independence than using the definition and intuition, because using intuition is kind of tricky and like really kind of sucks. So I'll give you a better way to look at that. And so first, the motivation, like the reason we're learning about this stuff is after we finish this unit on probability, we're pretty much going to spend the rest of the semester discussing something called statistical inference. And this is where we're going to use a sample characteristic to infer a characteristic about a population. So, for example, you do a poll and you find that, we'll pick somebody not offensive, 6% support Gary Johnson. I don't know. It's an election year, so this is all this in the news. And you want to say, okay, in that poll, 6% support Gary Johnson. How much can I say that this generalizes to 6% of the population? And you're going to use probability to be able to quantify these things, like well, how certain you are that you've got the thing right. So if you take two different random polls, are you going to get the exact same number from them? Definitely not. So you take two different simple random samples, the characteristics are going to be different comparing these two groups. And so we're going to use the statistics stuff, the probability stuff, we're going to learn how to talk about, okay, well, are these differences so big that something weird's going on, or are these differences okay? And other things that could happen is sometimes you could see an effect in the sample that isn't really present in the population, or see no effect when one really is present. So seeing an effect in the sample that really isn't present, say something like, a good example of this might be, there was an example about cancer and coffee, right? That drinking coffee led to cancer, but that wasn't actually present.
Was that from California?
No, it wasn't in California. It was when they separated out smoking, they found that the effect was actually the other way. Or there might be an effect and you just don't see one because your sample size isn't big enough. So we're going to just need to acknowledge and recognize the probability that these things are happening. So I say acknowledge and measure the probability of these things that was supposed to be an exclamation mark, not a question mark. And that's what we're going to use some of this probability stuff for. This is kind of a personal story, but when I first started to care about statistics, I'm really a mathematician. I got a master's degree in math here, and I first started to care about statistics when I read a book about diet and exercise called Why We Get Fat and What to Do About It. And in this book, this guy talked about all this statistics done really, really badly, so I didn't know enough math to know how to do all that fancy statistics. And then I bought a book called Statistics Done Wrong, and talk about how people who are scientists actually just did statistics incorrectly and then published their results and still got away with it because people reading their papers didn't know enough to say that they were wrong. And one of the examples it had in there was this kind of example. And it's kind of a cool question. So this is a true story. There has been some controversy over the use of mammograms to screen for breast cancer. And the reason that this is because there's a pretty high false positive rate. You know what a false positive is?
Yeah.
So it means you don't have cancer, but you still have a positive test result. That's what a false positive is. And some argue that the danger of these false positives, and these things usually result in unnecessary treatment, outweigh the benefits of early detection. And so we assume that only 0.8% of women who get mammograms actually have cancer, and in 90% of the women with breast cancer, the mammogram is going to find it correctly. So how many people that have breast cancer is it not going to find that? 10%. 10% of people are going to have cancer and it's not going to find it. And then the kicker is that with people that have no breast cancer, about 7% of them are still going to get a positive reading.
There's the other 10%. 10% almost.
Yeah, but it's a wholly different group. But you have the group that has cancer, group that doesn't. So you have the has cancer, has no cancer. Which group is bigger? Has no cancer is huge, right? Has cancer is kind of small, right? And in that has cancer group, 90% have a positive test, 10% have a negative test, right? In the has no cancer group, only a little chunk of it, 7% get a positive test, right?
If it's large.
But it's a big chunk is the problem. So since there's a big chunk of people here, the 7% of big chunk of people is a large number of people. And so the question you want to ask yourself probably is that because there are so many false positives, what's the chances that you're one of those false positives if you have a positive test? So the question, after we finish this chapter, specifically on Friday, we're going to answer this. So if you get a positive reading, what's the chances that you are actually sick? And it's not 90%, it's actually quite low. So it's kind of a thing that if you have a positive test result, maybe you shouldn't worry so much because it probably is a false positive. Depends on the test too, because different tests are different. But I think that breast cancer is pretty bad, and I think that also, what's the common cancer for men? From ignorance here. Prostate cancer, I think, also has the same problem with it, the same problem with the test. Okay, so we're not going to do that now, but we will do it later on, I promise. Okay, so some conditions for probability. So probabilities are numbers between what and what? 0 and 1. The sum of the probabilities over all possible simple events is equal to 1. So in other words, the total probability for all possible outcomes of a random circumstance is equal to 1. Okay. So suppose I have A, B, and C, and they're disjoint events. What does disjoint mean? Do you guys know?
Different?
Different is a good way to think about that, yep. Different meaning there's no events in common. As in A, B, and C are totally separate from each other. They don't ever overlap. So explain whether each of the following sets of probabilities, explain whether they're possible. So can P of A be a third, P of B be a third, and P of C be a third? Yes. So why is that okay?
Because there's 3 possible events and each of them have a 1 in 3 chance of happening.
Yeah, well, it's okay because P of A plus P of B plus P of C is equal to 1, right? As in they don't add up to something bigger than 1. So here's a picture of what that looks like. If you have like your overarching all possibilities in the box, maybe this is A, this is B, this is C, and they encompass everything. So A, B, and C cover what's called the sample space. Did I use that word with you last time? Okay. I don't know if your book uses that word, but it's nice to refer to all the different possible things. That's called the sample space. Did the problem say that A, B, and C had to cover the sample space? No. Okay, but in this case they did, and that's also okay. How about this one? Could P of A be a half, P of B be a half, and P of C be a quarter? No. And no, because P of A plus P of B plus P of C, what does that equal when you add them all up? Which is bigger than 1. So, and if they had nothing in common, then it wouldn't be possible for that to add up to something bigger than 1. Would less than 1 be okay? Yeah. This one almost tricked me the first time I did this problem, because I was like, oh, must add to 1, but they didn't say that A, B, and C had to be everything, right? So yes, this is okay. And that's because P of A plus P of B plus P of C is, I think, 3/4, right?
Yeah.
Which is less than 1. So if you had your sort of A, B, and C divided up, you know, there's A, there's B, there's C, and here's some other stuff you didn't account for yet. But they're still disjoint. And being able to make that conclusion did rely on them being disjoint. If they're not disjoint, you can't make the same conclusions. In that case, they all could be possible because maybe some things like A and B in part B have some stuff in common. You just count them twice. Okay. So common stuff with probability are things with coins and flipping dice because that's a really easy situation to picture. So suppose you flip a coin 3 times and you record if it's like heads or tails. I want you to list the sample space of all possible outcomes and then find the probability of flipping 1 tail, call this B, and the probability that you will flip at least 2 tails, call this C. So first of all, let's figure out how many things are in the sample space. So S has, think about it, how many possibilities for the first flip? 2. How many possibilities for the second flip? 3rd? And they multiply. So 8. It has 8 simple events. That's the size. You're looking for 8 things. And one thing I think it can help you, I can teach you in this class is how to be a little bit systematic listing these things, because it's a skill that you actually have to learn. So start with like all one thing. So how many ways can you have all heads? Or just one way, right? You have heads, heads, heads. That's the only possibility for all heads. And then just add in the tails one at a time. So I personally start by saying, okay, it could have been heads, heads, tails. And then I just kind of migrate the tails into a different spot. I could have been heads, tails, heads, right? And what's the other possibility with one tail? Tail, head, head, right? Is that all the possibilities with just one tail? I think it is, because either you have tails in the last, middle, or first, right? Okay, now there are other things you could have 2 tails, right? So let's say heads, tails, tails. What's another one?
Tails, heads, tails.
Tails, heads, tails. And then the last possibility would be?
Tails, tails, tails.
Yep. And then finally, you could have all tails. But do you see what I mean by like, think about it as no tail, 1 tail, 2 tail, 3 tail. Like think about it in terms of like get all the 2s, 1s, all the 2s, and then get all the 3s. Okay. And are there 8 things there? Yeah, okay, great. So the probability of event B, so B is picking exactly 1 tail. How many of those things are 1 tail? 3. Out of how many total? 8. And I think that most of my answer keys have fractions, so feel free to give fractions and decimals, but you know.
Which we can leave it as
You can leave us 3A's. Okay. P of C, so at least 2 tails. So at least 2 tails means what? So 2 is the smallest, so that means 2 or more. Does that make sense? 2 or 3. So how many of them have 2 or 3, 4? If you do leave fractions, let's reduce them to lowest terms because, you know, you are in, like, college now. I know, right? Especially 4/8, guys. Come on. Sorry, the sarcasm was not... Sarcasm was a little bit intended. I have sympathy for things that are not divisible by 2. When you can't reduce by 2, I start to have, like, come on. You can, it's even numbers. Divide. Okay. Okay. So complementary events. So how do you write the complement of an event?
AC.
A with a C, little superscript of C. And what is this set AC? It's all the events that are not in A. So together, A and A complement make your whole sample space. So if I have a picture, this is my event, that's my A bubble. All this stuff outside of it is my A complement stuff.
And is that the same as saying A plus AC is 1?
Yeah, so you can say the probability of A plus probability of A complement is equal to 1 because they're disjoint events that cover the whole sample space. Yep, exactly. You can't say without the P's there. Does that make sense? Mm-hmm. Okay. So I don't know how many of you play with decks of cards for kicks, but assuming we're not playing with jokers, there are 52 cards in a deck. How many suits are there? 4 suits of how many cards each? 13. Of 13 each. So you will need to know some of that stuff for like your homework and quizzes and things. Okay, suppose you're drawing cards from a standard 52 card deck. Let A be the event that you pick a heart. Find the probability of A and the probability of A complement. So what's the probability that you pick a heart? How many cards are hearts?
13.
Out of how many total cards?
52.
Great, which officially is 1/4, right? Okay, how about P of A complement? So that's the probability of not heart.
To subtract.
You can do 1 minus P of A or 1 minus 1/4, right? Which would be, you also could think that there are 39 out of 52 that are not, right? Same way? Okay. All right, then back to this whole mutually exclusive and independent thing. So mutually exclusive really is actually significantly easier to think, like, to test than independence. Independence is tricky, mutually exclusive is not. So 2 events are mutually exclusive if, who remembers? They do not share common simple events. Or you can think about that as they have nothing in common. It's like if you're rolling a die, the events of rolling an even and rolling an odd are mutually exclusive because you can't be both at the same time. That's what mutually exclusive means. Is an event and its complement, are those mutually exclusive events? Yeah, because you can't be in both at the same time. In a picture, like a little Venn diagram, if you have like a picture of your events, there's your event A, there's your event B, there's nothing in the middle. The way to write that mathematically, and I might do this sometimes, is like this. Okay, there's a lot of symbols there. Have you guys seen that little upside down U before? So that means intersect. When you look at where those two things intersect, this thing is called the empty set, and that means there's nothing. It's a fancy way of saying when I look at what's in both of them, there's nothing in there. Okay, if two...
Intersect is not similar to intercept, like y-intercept, right?
Nope. Intersect is different than intercept. Yep. Make sure I enunciate correctly. Yep. Okay, if 2 events are mutually exclusive, we've kind of been using this rule all along, then the probability of either A happening or B happening is the probability of A happening plus the probability of B happening. We kind of use that rule with complements, with the complementing thing a little bit. Okay, what about and? If 2 events are mutually exclusive, what's the probability that they both happen at the same time? 0. Does that make sense? Because think about this as A is the event that your die is even, B is the event that the die is odd, like when you do one roll. So can your die be even and odd at the same time? No. Versus being even and a 6 or something like that. So, okay. All right, suppose we're drawing from a 52 card deck. Let A be the event that you draw a heart, B be the event that you draw a club, and C be the event that you draw a face card. So which events are mutually exclusive? Okay, are A and B? And we'll say, yes, you can't be a heart and club at the same time. Okay. How about A and C? Are there things that are in both the event that you draw a heart and a face card?
Yes.
Yes, so in that case, no, they're not mutually exclusive. Because, I don't know, we'll say Queen of Hearts. Is in both. And if there's overlap, they're not mutually exclusive. How about B and C? Yeah, also no. Same reason, right? Things like Queen of Clubs in both. Okay. Alrighty. So I didn't ask you to find P of A and C or P of B and C yet, but can you find P of A or B? Because they're mutually exclusive, you can say that's equal to P of A plus P of B. And we will have a rule that we're going to learn tomorrow that generalizes to events that are not mutually exclusive as well, and works for this too if you forget. So what's the probability that you are a heart?
13 out of 52.
And what's the probability that you are a club?
13.
So I think that's going to be a half in the end, isn't it? Okay. How about P of A and B? So saying probability of being a heart and a club. That's not possible, is it? You draw a card, you can't be heart and a club. That's going to be 0. Okay. So something else we're going to talk about with probabilities is supposing you know some condition, it might change the outcome of something occurring. So for example, suppose I know you have cancer, that means that the probability that you have a positive test result probably is going to be higher than someone who doesn't have cancer, right? So that's something called a conditional probability. Sometimes knowing an event occurs does change the probability that the other event occurs. It's related to independence. So this little PA line B, how you read this is the probability that A occurs given, I should say given, not give, given that B occurs. And the whole given that business means that you know B happens. What's the probability of A happening when you know this? That's what this is saying. And this thing is not a commutative thing, okay? Like flipping the order does actually change the outcome. So P of B given A is the probability that B occurs given that A occurs. And personally, I don't know about you guys, but like when A and B mean things, I have to actually write down like what A is and what B is so I can like dissect what's going on here. But it's read A given B or B given A. Okay, so A is the event that you have some disease, and B is supposed to be the event that I meant to fix this and I guess I messed up because I have it in my notes and forgot. The event that you have a positive test result. What do P of A given B, P of B given A? What do these things mean? So P of A given B. So what is A?
You have disease.
So probability of disease given.
That you got a positive test result.
So this is the probability you have the disease if you have positive test result. And I think that's the question we want to answer with that first question that I asked on that first page, right? Suppose you know you have a positive test result, what's the chances that you actually have that disease? How about P of B given A? Let's see if that means the same thing. Probability of positive test given disease. Is that going to mean the same thing? No. This is the probability you have a positive test result given that you have the disease. And I think we were told that on the first page, weren't we? I think the first page says something like that in 90% of the patients who have 90% of women who have breast cancer get a positive test result. So like in that question, this thing was equal to 90%. That's what it was equal to 0.9.
Q.
That's a Q for like the question on the first page. That was equal to 0.9. And what is P of A? What does it mean?
That you have the disease is
Mhm.
0.8.
The probability that you have disease? Yep. From that question we did earlier, that was 0.008. I think this was 0.8%, right? Yep. And P of B, that is the probability of positive test. And that one I don't know if I specified that well enough in the previous question to give you a, but are these things are actually different? Does it make sense that P of A given B is different than P of A? That if you have a positive test, this probability will be different than the probability you actually just have the disease. So knowing that thing might change it. Okay. Oh, that didn't work. Worse in your notes though, right? Okay. So, based on a survey of nearly all 9th and 12th graders in Minnesota Public Schools, 98, I was not in that grade at that time, a total of 78,565 students reported proportions admitting that they had gambled at least once during a week during the previous year. So there's your sample size. And it was discovered that these proportions differed considerably for males and for females. Men gamble more. One more reason why women are awesome. So, and this was, the numbers that I have listed here specifically are for 9th grade boys. So 22% of 9th grade boys and 4.5% of the girls admitted to gambling weekly. And these things you're asked to find here really are just for 9th graders. So what's the probability that you have a gambler if you know you have a boy? 0.229. It's just that percent as a decimal form. And what's the probability that you have a gambler if you know you have a girl?
1.0.
Exactly. And I don't think we know how to find the probability that a random person actually is a gambler in general because we don't know how big the populations were girls and boys. So, but that's all that one is saying. Okay, back to this independence thing everybody loves to hate. I hate it too a little bit. So, two events are independent if knowing A occurs tells you blank about B occurring. It's opposite. Tells you nothing. In other words, A does not depend on B. Like A happening does not depend on B, which means if you know B happens, if you know A happens, nothing happens to B. But this logic can be really tricky in lots of situations, so here are other ways to test for independence, and I think it's better to use these rules instead of relying on your intuition. So use the rule and then check and see if you can justify it with your intuition a little bit. So P of A given B is equal to just P of A. As in, knowing B does not change P of A. That's what that means. That's what that condition says. Okay, no B happens, but it doesn't affect it. How do you think that rule would generalize for P of B given A?
Same thing with
Same thing, but with B, right? Because the order of the A and B reversed, right? So knowing A gives no information about probability of B. And this is the rule you definitely use the most frequently, that P of A and B is equal to P of A times P of B. And two events are independent. This if and only if means that you can use this to check if these events are independent. So if this is not true, then you know the events are not independent. If it is true, you know that they are. So here's how you check for independence by finding P of A and B, which might involve like listing the events in A and B, and then P of A times P of B. If they're equal, then if not equal, then. So fill in my thens. If these two events are equal, if P of A and B is equal to P of A times P of B, then the events are what? Then they're independent. If they're not equal, then they're not independent.
So if we say that they're not independent, does that mean that they're necessarily dependent or no? Like if something is.
Yeah, and it's a great question, because sometimes the opposite of not is not as you think it is. Like the opposite of guilty is not necessarily innocent, right?
Right.
I think in this case you can say that they are dependent. I think that's okay. Yeah, I'm pretty sure that that's okay. If they're not independent, I think that the opposite of that just is that they're dependent.
Right.
Yeah. I think that's totally fine. Good question. Okay, so let's try that with full examples. So when a fair die is tossed, each of the 6 sides numbered 1 to 6 is equally likely to land face up. 2 fair dice, 1 red and 1 green, are tossed. Explain whether the following pairs of events are mutually exclusive, independent, both, or neither. Okay, so mutually exclusive, can I use ME for that? Okay. Mutually exclusive if A and B have no events in common. Is that true?
Yes.
Yes, that's true. Yep. So they're yes. A and B are mutually exclusive. Independent. Let's find it using probabilities. What's the probability of A and B? And the kicker is that A is the red die being green and B is also the red die being 6. So can those two things happen at the same time? No, so that's equal to 0. If they said red die, green die, then it would be okay. Okay, how about what's P of A times P of B? So what's the probability of having a red die? 1 out of, if you roll a random die, that is, not just in this, like not only considering A and B as possibilities. If you roll a die, the probability of getting what's the chances of the red die being a 3? That's 1 in 6, right? Chances of the red die being a 6 is also 1 in 6. Multiply together, you get 136. So do those two things equal each other? Does 0 equal 136? No. So therefore, they're not independent, i.e. they're dependent. That's how I use the rules to check. And the way that was this was explained on the first day is that if you know the red die is a 3, the red die can't also be a 6, and the probability of that happening now is 0. So knowing that A happens has changed B happening. It's no longer 1/6, the probability of that happening is now 0. So, but I think it's easier to use the multiplication rule thing. How about red die is a 3, green die is a 6? So are they mutually exclusive? No. We can have both happen at the same time. Okay, how about independent? Ooh, what's the probability of A and B? Okay, it's getting a little bit ahead of ourselves here, but if you were to like list out all the possible combinations of like red die, green die in order, how many would there be? How many choices for the first die?
6.
How many for second die?
6.
Total of
36.
36. Okay? We're going to do that in the next example, actually. We're going to actually list most of them. And of those combinations, how many of them are going to be red is 3, green is 6? I think just one of them, because we're counting them in order. We're not going to count 6, 3. Does that make sense? Just count them with 3, 6. That would be 1 out of 36. We'll talk about how to list that in the next example, I promise. Okay, so that's kind of like the work for figuring out that was 1/36. What is P of A times P of B? What's the probability the red die is a 3? Probability the green die is a 6. So that's also, so since those two things are equal by that little rule I just told you, are they independent? Yes. Okay. This one on yours as well. So red and green die sum to 2, and B is that the green die is a 2. Okay, so are they mutually exclusive? Can you be both? Yes, exactly. So yes, because you cannot be both. Me, yes. Read your notes 5 years from now, you're like, what was me? Okay, independent. What is the chances that the red and green die sum to 2 and the green die is a 2? That's 0, right? If your 2 die add to 2, what do they both have to be?
1.
Both have to be 1, right? Because there's no die that has a 0 on it, yes? Versus P of A times P of B. So having the red and green die sum to 2, that means you have to get a 1, 1, right? That happens with probability 1/36, right? Times the probability of the green die is a 2, that's 1/6. No multiplication necessary to know that whatever that is not equal to 0, right? So since P of A and B not equal to P of A times P of B, these events are not independent, or you could say dependent. I think it's 1/216. I think 36 times 6 is 216. I just have 6 cubed memorized. I'm not actually that good at arithmetic. Okay. Who systematicness? I probably would never make you do this in practice, so we're just going to talk about how to list these things. So we have the same thing, we have, except for this was a red die and a black die. So 1 black and 1 red, and you record the outcomes in order. So in this one, we have black first and red second. How many different things are going to be in this sample space? How many choices for the first die? 6. How many for next die? 6. If you're going to list them all, you're going to have to list 36 things, right? So you're recording like the pairs of die that comes up, like 1, 1, 1, 2, 1, 3, 1, 4, etc. So let's just list them like a little bit systematically just for a few. So the first thing you could have had is you could have had 1, 1, right? What else could you have that would begin with 1 and do it in some kind of systematic order? 1, 2, what else? 1, 5, 1, 6, and that's it, right? What would be the next group you'd want to list? 2, yep, so 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, where the first number is the number on the, in this case, black die, second one is the number on the red die. Yeah.
So you would still do all this even though we're trying to find them to sum to 10?
Aha.
Yeah.
We'll get there, okay? Because there are lots of ways to sum to 10. So this says to list all the events in the sample space S, all the possibilities, and then list the stuff that's in A, B, and C. So A is the event that you've got red is even, B is the event that the black is odd, and C is the event that the die sum to 10. So how many more things are going to be in here? We have 6, 6. There's going to be how many more groups of 6? 4. What's the next one? The one that starts with 3. Let's just do it. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, and then 4, 1, 4, 2, 4, 3. You see this yet? Ugh, I don't know why I did this to myself. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and then 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. You see, being systematic does definitely help, right? Whoa. Holy moly. Okay, A. What is the event A?
Red die is even.
Red die is even. Is the red the first or second?
Second.
Red is the second one? Okay. So let's just look at the above thing and let's just underline them. So that's this one. How many of them are there? How many of them are there going to be? I think it's going to be exactly half of these, right?
Yeah.
To be 18 of them. That's a lot, yep. Okay. B is the event that the black die are odd. So that's the first die, right? Okay, so let's underline those in a different color or form. So let's do squiggles and I'll do red. So that one, that one, that one, that one, that one, that one. All the ones, skip those. So this one. Skip all the 4s. Okay. How many of them are there?
18.
18 of those as well, yep. 18 of squiggles. Are the events A and B mutually exclusive? Is there no overlap? There is overlap, so they're not mutually exclusive, right? Okay. And then C, last event, this one we can actually list, it's not too bad. So C is the event that the die sum to 10. So will any of the 1s sum to 10? Any of the 2s? Any of the 3s? Get close, right? How about the 4s? 4, 6 will. Who else? Any of the 5s?
Yeah.
5, 5, yep. And then is there any of the 6s? 6, 4. Okay. I know, right? I know. Okay. Part B on this question, which is on my next slide, but I kind of want that list there for my next question, asks, find the probability of A and B, right? Okay, probability of A and B. So look at that picture. How many things are underlined in red and blue? Red, I think red and blue is just 9 of them, right? 1, 2, 3, 4, 5, 6, 7, 8. Do you agree with 9? So 9 out of 36, which reduces to how much? 1 out of 4? Yep, or 0.25, same thing. Okay. And the next part of that question says, are A and B independent? How would you check? What do you find? Times. Exactly. So what is the probability that event A occurs? How many things were in event A?
18.
Out of 36, right?
Yeah.
Times another,
18, 36.
which is equal to half times a half, right?
Yeah.
Or 1/4. So since those two things are equal,
It's independent.
yes. Okay. And your part C says to find the probability of A and C. So my A is the blue, and C, those are just 3 of them. That was what, 4, 6,
So 4, 6.
5, 5, and 6, 4. So how many things are in both A and B? 2. So that's 1/18th, right? Okay.
Wait,
Yes? You're good? Okay. Yeah, remember event A was the red die being even, which is the second die, right? And event C was the numbers summing to 10. Okay. And I think this one also says, are A and C independent?
Yeah.
Okay, well, let's check using the definition. So what is probability of A times probability of C? So 18 out of 36, and C is,
36.
and definitely reduce those before you multiply, okay? Half times 1/12, great, which is 1/24th. So is an 18th equal to a 24th? Close, but no cigar. Sorry. Do you like that way of checking for independence better?
Yeah.
Yeah, okay. So no, not independent. Okay. So suppose you roll 2 dice, 1 black and 1 red again, and you record the outcomes in order. Oh, we did this one already. What am I talking about? I know that. Okay, there we go. A and B are mutually exclusive. Use one of the rules given on the previous page to determine whether these events are independent. So if they're mutually exclusive, let's use the AND rule. What is P of A and B? That's equal to, if they have nothing in common,
0.
that's equal to 0. I probably have to assume that these are something called non-empty events. P of A times P of B. And we're assuming that, like, as in A and B can't be impossible things. What kind of number is going to come out, assuming there's actually stuff in both A and B? Positive, negative, 0?
Greater than 0.
Greater than 0. Also less than 1, right? So can those two things be equal if one is equal to 0, one's bigger than 0? Yep. So thus, A and B are not independent. So what that really means is that if you're mutually exclusive, you know you should get that the events are not independent. Does that make sense?
Oh.
Always.
Yeah.
This is like
Yeah,
for
It's
always.
always gonna equal 0, yeah.
Exactly. That means P of A and B is always going to equal 0. It's not special to this case. I didn't even tell you what A and B were. Right? They can do whatever the heck I want. So if mutually exclusive, that's not independent. That I don't know if that reverses or not. That's not always clear. Maybe it will, maybe it won't. But that's why. Okay, so we're going to learn some more rules for finding P of A or B and P of A and B next class. But for now, if things are not mutually exclusive, you can find the probabilities of unions, which is ors, or intersections, which are ands, by just counting the events. Like the thing with the whole hearts and clubs was easy because you can't be hearts and clubs at the same time. But the next one, we're going to find one where there's actually some overlapping and talk about how to find that probability. So suppose you draw a car. That'd be amazing. Suppose you draw a card from a 52 card deck. And let's let A be the event that you draw a heart, and B be the event that you draw a club. That's dumb. This is easy. What's P of A or B? Are these things mutually exclusive?
No.
Do they have anything in common? Heart, club.
Except like the deck cards.
Hmm?
Except like that they're both hearts.
So there's nothing in common, which means they are mutually exclusive. So I think that's just going to be a half, isn't it? 13 out of 52 plus 13 out of 52, which is a half.
Yeah.
Remember that ME means they have nothing in common. And ME is what lets you do that turning or into a plus. That's what allows that to happen. So given that they're mutually exclusive, what's P of A and B? Can you be a heart and a club at the same time?
No.
No. Okay. The next one actually has some overlap. This one was just an easy one. Okay. A is the event you draw a heart. B is the event you draw a face card. So there are hearts and face cards, right? Okay, we'll be a little bit more careful here. We can't just say P of A plus P of B. Okay, so first of all, how many hearts are there?
13.
13 out of 52. How many face cards?
4.
There are 12 total, right? How many of them are already in that pile?
3.
There are 3 of them already in that pile, right? Because there's the Jack, the Queen, and the King of Hearts. So how many left could you have to account for? 9 out of 52. Does that make sense? So this is the hearts, right? This is the non-heart face cards. Because if it was just face cards, it'd be 12, right? But there's 4 of them that you already counted in the first thing.
3.
So that ends up being,
9.
3 that you already counted, yes. That's up to 21 out of 52. My point with this is just kind of avoid double counting by thinking, is there some of the second thing already in the first thing? How about P of A and B? How many things are both hearts and face cards?
3.
3 out of 52, which reduces to 1/13, right? No.
14.
That'd be 4 out of 50.
114.
Oh, I just failed today.
And the first one is 22 out of 52.
What was just a good day?
11:26. Thank you. I said 8 on my thing. I must have also thought there were 4. Anyway, yeah. Okay. But do you see what I mean about accounting for things that were counted?
Yeah.
Yeah, okay. We'll learn a more general rule tomorrow that lets you take care of that as well. All right, last thing. So you have a sample of 7,000 naturalized U.S. citizens. We have the events given in the table below. Suppose we pick somebody at random. Find the probability of the following events. So event A is that somebody's under 20. Event B is that they're 30 to 64. C is that they're 50 plus, and D is that they're 65 plus. Okay, so
Well,
yeah,
sorry.
those things are definitely not mutually exclusive. You can be in category C, D, and category C, right, at the same time?
Yeah, no,
Okay.
I thought you were talking about section B on here, not letter D. on
Oh, yeah,
there,
letter,
so never
yeah,
mind,
yeah, okay. So what is the probability that A occurs? What's the chances you're going, if you pick a random person, you're gonna pick someone who's under 20?
2450 out of 7,000.
2450 out of 7,000. Yep. Which ends up being 0.35. Your part B asks for the probability of a complement, which is not being under 20, right? As in being over 20.
So it would be 1850 equals 20.
Even easier.
7,000 minus.
1 minus
Minus
0.35,
Yeah.
right? Which works out to be 0.65. What you were saying you were going to do, as in like add up all.
Take the long route.
Yeah, that actually might not work as well because there are people that are in D who are also in C. Does that make sense? Because you can be 60, if you're 65 plus, you're also 50 plus, right?
Yeah.
So that's one thing that is a little bit tricky with that. You probably can't actually do it that way because of that little trickery there.
That would explain why.
Why you didn't get the same answer? Yep. Okay, part C asks for the probability of B. That one's not tricky, right? That's just 18.
50 over 7,000.
Yep. That ends up being 0.158. Okay, and D, how about P of A? I guess I probably meant to say or. I meant to say, because and would be impossible.
Zero, right?
I'm sure I meant to say or, because and is probability 0.
Yeah.
Are those events mutually exclusive? Is there any overlap between under 20 and 30 to 64? No, there isn't. So you can say that this is P of A plus P of B. And that was 0.35 plus 0.158, right? What's that add up to? 0.508? 608. No, I think it's
It's 0.508.
0.508. Okay, awesome. Yes.
For C,
Did I calculate it wrong? What'd I get?
0.264.
I boo-booed then. 0.264, which will change this. And that makes this 0.614, right? Okay, all right. Let me just pause the recording part of it.